Right, just a fair reminder, it is Tuesday, so the exam is due tonight by midnight. There is a cutoff, so I think it's 10:50 or 10:45 p.m. will be when it won't let you access the testing more because you don't have enough time to finish the exam. But other than that, we're kind of in the home stretch at this point. Test 3 is going to represent the hardest test you take until the final exam. The next exam is pretty straightforward, especially if you're getting the Test 3 material. So, what questions y'all got for me out there? I'm not seeing any viewers, so until somebody shows up, I'm actually going to kind of work on a side project. So yeah, I'll take a look over every now and then. But yeah, if you don't have any questions, I'll just kind of work until about 11:15. So a question just popped up. We'll be working KQ. Yes, so you'll definitely be solving a problem where you're given KQ and you're asked to find concentrations at equilibrium. And I think you're given two flavors of that. Oh, I'm sorry, I misunderstood. So I'm looking at the problems right now. So the working with KAQ problems where you add and subtract to find the new KAQ expression based on the old one. Yes, there will be an example of this, but it's a multiple choice question. So for number 3 in the packet, I'm going to bring that up so people can see it. What is KAQ of twice the first reaction is added to the second reaction? So to handle this, easiest way to look at it, if we're going, we've got twice the first reaction, so we got 2 times this whole reaction. And twice the first reaction is added to the second reaction. So we've got 1 times the second reaction. So the easiest way to work these types of problems is take whatever you're multiplying each reaction by and raise that k to that power. So this would be k to the second power, k2 to the first power. And then multiply them together. So your final expression here would be k1 squared times k2. And let's say if we said, so let's say we switch around, what if twice the first reaction is subtracted? So instead of saying added, we said subtracted. Well, subtraction is a negative, so you would just have a negative there. That would give you a -2 there. And that would be, come on. k1 to the -2 times k2, or k2 divided by k1 squared. So that's how you work those types of problems. You look at the algebra that's being applied to each one, raise the k's equilibriums to that power, and then multiply them together. But again, there's only going to be one problem of that on the exam, and it's just a multiple choice question. This is relevant when we start getting to electrochem, so it's kind of putting the framework down there for electrochem, but we're not quite to a point yet where we're really going to use it. But it is relevant to talk about it now in terms of equilibrium, because we are talking about equilibrium. For the very hard equilibrium problems, you're not going to be given anything that hard. The big thing with that is, can you set it up? And if you can set it up, everything from there is algebra. So for the hard equilibrium problems, make sure you can set them up, but necessarily solving that quadratic and getting the numbers that are in there, that's an exercise in algebra, and that's not really what this course is testing you on. So traditionally in a seated course, what I would do is we would do the very hard problems, and we would only work to set it up. We wouldn't actually work to work out the numbers. Generally, just hand out the roots. And if students can get to the point where their IC tables are filled in, they've got the quadratics set up, and their principal could solve it, they see that really the only thing that makes these problems hard is the algebra. It's all the same concept. And this, again, is meant to start as framing for test 4. Test 4, you're going to be working with IC tables a lot, but they're very simplified IC tables because we're only doing acid-base equilibrium. Yeah, you would definitely never see anything like those very hard equilibrium problems on the exam. Those are just tedious. There's lots of points where you can make mistakes in the algebra and just in terms of how you FOIL or how you rearrange and combine like terms. But again, you should be able to set them up just fine. Yeah, glad I could help. Yeah, glad you're getting a lot of use out of Excel. And again, it's kind of sad, but that will probably be the most useful skill you take from this course. Thanks for letting me know. I'm glad you're enjoying the course. And you, yeah, please have a good day too. Thanks for showing up. Looks like it's pretty much you today, so you can get a lot of work done on this little side project. Oh, look, someone else showed up. You can go over one problem on each page, 25, 30, and 35. All right, give me a minute to write this down. All right, so gotten a request to do the Hess's Law, so let me switch it over to the Hess's Law problems. So we'll start with the first one on each one, this ethylene problem. The C2H4 plus 3O2 goes to 2CO2 plus 2H2O. And our delta H1 here is minus 1323. Two H2 plus O2 goes to 2H2O. And this is a delta H2 of minus 483.6. We have C plus O2 goes to CO2, delta H3 minus 393.5. The last one, 2C plus 2H2 goes to C2H4. And this is the delta H we want to solve for. So two ways you can approach this, adding and subtracting or writing out the Hess's Law expression. If we write out the Hess's Law expression, and I'll do this in red, the delta H here equals twice the enthalpy of H2O plus twice the enthalpy of CO2 minus the enthalpy of C2H4 plus 3 times the enthalpy of O2. And this whole thing equals minus 1323, 1,323 kilojoules per mole. Second one, delta H, twice the enthalpy of H2O, minus the enthalpy of O2, plus twice the enthalpy of H2, equals minus 483.6. For the third reaction, delta H is the enthalpy of CO2 minus the enthalpy of carbon plus the enthalpy of O2. For the last one, delta H equals the enthalpy of C2H4 plus, or minus, twice the enthalpy of H2 plus twice the enthalpy of carbon. So that's the first step, is to write your Hess's Law expression for each reaction. Next step is you cancel out everything that's zero. So these are the diatomic gases and pure elements. If you see more than one element in a compound, it's definitely not going to be zero. So O2 is going to disappear. So is H2, and so is carbon. So if I erase these, and definitely for the last reaction, everything else is going to cancel out. I get that twice the enthalpy of H2O is minus 483.6, and the enthalpy of CO2 is minus 393.5. So I'm going to put these two numbers back into this equation. So twice the enthalpy of H2O is minus 483.6. Twice the enthalpy of CO2, that's 2 times minus 393.5. The one I don't know is the C2H4, so I can rearrange this so I make these switch sides. And I get that minus 43.6 plus 2 times negative 93.5 plus 1,323 equals the enthalpy of C2H4. The number you get for this is just going to get stuck down here because this is ultimately what you're solving for based on the final reaction. This isn't always true, but in this case it happens to work out that our missing enthalpy here, that C2H4, is the enthalpy we're looking for here. Now, to solve this for the Gibbs energy, we have the same problem here. C2H4 minus 1314 minus 457.2 minus 394.4. This is solved the exact same way. So the only thing I would do on the board behind me is just change out the numbers. So if you already have a solution worked out for one reaction and you go around and you switch it for the Gibbs, you just turn around and takes whatever your solution set was for the delta H's, put in your numbers for the delta G's, and that's how you would solve those. Now for the last page, you're going to notice that all of these correspond to previous problems. So we have this 2C, 2H2, 2C2, H4. This was the one we've already solved for. So we've already gotten the Gibbs and the delta H and the delta G for this reaction. So in order to figure out the delta S for this reaction, we just use the Gibbs relationship. So we get that delta G equals delta H minus T delta S. The delta H you calculated on page 26. This was on page 31 that you solved this out. You're given the temperature is 100 degrees C, which would be 373 Kelvin. So your delta S is just delta H minus delta G over T. Yeah, you're welcome. Number 5 on page 9. Make sure that's the correct number. 1, 2, 3, 4. So the KSP of lithium phosphate. I'll bring that up for people to see. So given the KSP of lithium phosphate as 2.7 to the negative 4, we're asked to find the concentrations of both lithium and phosphate at equilibrium. So to solve these types of problems, again, it's an equilibrium problem. We need our reaction. So we've got lithium phosphate, Li3PO4. Since this is a KSP, it's going to indicate that our reaction is a solid. Goes back and forth to 3Li plus PO4 minus 3 AQ. So we need our KAQ equals Q. So our KSP equals Q. Q in this case is lithium to the third power times phosphate, PO4 minus 3. And we need an IC table. Now again, we can ignore the solids because it doesn't appear in our expression for Q, so we just got lithium, phosphate, not given any starting concentrations. The change for lithium is plus 3x. Change for phosphorus is just x. So our in value is 3x and x. We're being asked to find the equilibrium concentrations. So if you're asked to find equilibrium, it's going to be these last two boxes. So we're going to have to use one of these two rows in this expression. Since we work this out entirely, we'll put it up here. So we get 3x to the third power times x. So this gives us 27 x to the fourth. So if we take KSP divided by 27 and raise it to the 1/4 power, that will give us x. Whatever number we get for x, in this case, the concentration equals x because these two rows are equivalent. So the concentration of phosphate in this case is just equal to x. The concentration of lithium is equal to 3x. To verify your answer, take these numbers, stick it back into your expression, and make sure you're able to recover the KSP. You're welcome. I'll give you about 4 more minutes. If there are any more questions, we'll head out for today. That looks like it's it for the questions today. So again, if you ever need help, please feel free to send an email. We've got the live streams this week. So third exam is due today. Again, it is the hardest exam you'll take. Test 4 is substantially easier. It's basically what we're doing right now with just peripheral information added to it with much simpler equilibrium problems. So yeah, it looks like we're closing on the home stretch. So thanks to everyone who was able to make it today, and I will talk to you all tomorrow.